Hi everyone, we're back with our next lesson on limits approaching positive and negative infinity. We did a little previous lesson to kind of warm our brains up on what exactly infinity is or means. And so we're going to get into some of our examples. So the first example here is to take the limit as x approaches infinity of 4x minus 3 all over 2x plus 1. So we have a rational function here. And so this is not quite like our earlier examples on the last video where we were doing linear functions and quadratic functions, and the answers just came out nice and neat when we plugged them in. Rational functions are a little bit different because they pose more hiccups for the mathematician in that they can have horizontal asymptotes and vertical asymptotes, and we're going to get into those graphs in another lesson, but I'm going to choose all rational functions today to kind of complicate things, I guess, as we do limits to infinity. Today we're just going to go through the skills of it. So the first step to doing a limit at infinity is to plug it in, just like we always did. So what I'm going to do is I'm going to take infinity, I'm going to insert it in for these x's. So we're going to have here 4 times infinity minus 3 divided by 2 times infinity plus 1. And now I'm going to exercise something called the principle of dominance. You may have studied this in your pre-calculus class. The principle of dominance says that when dealing with infinity or negative infinity, you're really focusing on the term of highest power. So in other words, when you take 4 times infinity, that's going to give you infinity. And this minus 3 just has really no impact on this really large number here. So the principle of dominance would say, just take 4 times infinity, and that's infinity. On the bottom, same thing. 2 times infinity is infinity. You add 1, that 1's not having any bearing on this, so we're just going to say infinity. So we have infinity over infinity, which we know from our last video is undefined. It is not 1. Okay. In the recipe for limits at infinity, the next thing that you do when you get something undefined is you divide each term. There are 1, 2, 3, 4 terms in this rational function. You divide all 4 of them by the highest power of x in the denominator. So you look at your denominator, boom, there it is. The highest power of x is right here. It's just a single x. The highest power of x is x to the first. So everybody, the 4x gets divided by x. The 3 gets divided by x. The 2x gets divided by x. And the 1 gets divided by x. That's step 2 in the recipe. Step 3 is to reduce. Algebraically, we're going to reduce this function. So 4x divided by x is easy. That's 4. These x's drop out. 3 over x doesn't reduce, so we'll just leave it. 2x over x out, and 1 over x doesn't reduce. So our last step in the recipe is to plug it in again. So now what we're going to do is insert infinity one more time for these x's. So we're going to have 4 minus 3 divided by infinity over 2 plus 1 divided by infinity. Now 4 is 4. 3 divided by infinity. In our last lesson, we talked about this, that a real number divided by infinity heads towards 0. So that is exactly what I'm going to do. 3 divided by numbers heading toward infinity. This quotient is approaching 0. Same with 1 over infinity. So the answer to this limit is 4 divided by 2, which is 2. Now we're going to talk more about what this means in another lesson, but for now, you just know that this limit approaches 2. The other thing I want to say is, why did we do this? I like to tell students, what the heck, why did we divide each term by the highest power of x in the denominator? Well, here's the reason. It's this infinity, when we first plugged it in, that's making this undefined. In other words, like infinity is fine. Infinity is infinity. But you put that infinity on the bottom, now we're dividing, and this is undefined. So when you divide everything by the highest power of x in the denominator, what you're ensuring is that your denominator will result in a real number, and you won't have division by infinity anymore. Anything that has a lower power of x is going to end up going to 0, but you're forcing the denominator to have at least one real number that doesn't involve an infinity. And for that reason, you get rid of division by infinity and you can get a real number final answer. In most cases. Sometimes you don't, but we'll talk about that later. Okay, example 2. Example 2 says, limit as x approaches infinity of the rational function 4x squared minus 3x plus 5 all over 2x cubed plus x minus 1. So we're going to go ahead and plug it in. Step 1 is to plug it in like we always do. So that's going to give us 4 times infinity squared minus 3 times infinity plus 5 over 2 times infinity cubed plus infinity minus 1. And the principle of dominance would say that I need only look at the terms of highest power on the top and bottom. So 4 times infinity squared is just going to be infinity. 2 times infinity cubed, also infinity. So we're undefined. So we have to move on to step 2, which is to divide each term, we have 6 of them, by the highest power of x in the denominator. The highest power of x in the denominator is x cubed. So we're going to divide each term by that. So this is going to give us 4x squared over x cubed minus 3x over x cubed plus 5 over x cubed all over 2x cubed over x cubed plus x over x cubed minus 1 over x cubed. Next we reduce. So when we reduce, 4x squared divided by x cubed is going to give me 4 over x minus 3x over x cubed is going to give me 3 over x squared. 5 over x cubed won't reduce, so we just leave it. 2x cubed over x cubed is just 2. There's that single real number we needed to eliminate division by infinity. X over x cubed is 1 over x squared. And then 1 over x cubed doesn't reduce. Final step is to plug it in. Getting hair all over the place here. So when we plug infinity in one last time, we're going to get 4 over infinity minus 3 over infinity squared plus 5 over infinity cubed all over 2 plus 1 over infinity squared minus 1 over infinity cubed. So this guy's going to go to 0. This guy's going to go to 0. And this guy's going to go to 0. All over 2 plus 0 minus 0. And 0 divided by 2 is 0. So the final answer to this problem for this limit is 0.